this for is going to produce a list, and this for is not going to somehow get rid of that inner list. It'll just still be there. And so that's not what we want, so we can go ahead and write a function that does what we want. It looks like this. So it's a function that's a whole lot like for, but the return type of this processor over the list is going to be returning lists, and we're going to flatten them all together. And so we can write that pretty simply, pretty directly, using just regular functional programming again. If the input to this whole thing is empty, then we just return an empty list. If we have a first value of the list that we're seeking over, the first element of our for, then we apply f to that, and instead of sticking it on the head of the result, of the recursive result, we append them. So this is the ampersand, or the @ sign in F sharp. We're just going to append the lists. So at the end of the day, we keep taking an element out of the list, applying our list generating function here, and appending it to the result of continuing down the list. And what's nice about that is it not only flattens layers, but it flattens as many layers as we want. I can now do this to a 3D list, or a 4D list, or a 15D array, and as many layers as we want. They always get flattened down to a single list at the end. And so using this pattern, we can write for loops that flatten all the way back up to the top. And the final example is logging. And this is one of those ones that's really interesting in Haskell, because Haskell writers put themselves in a weird bind where you can't have side effects anywhere. You can't just print out in the middle of a function. You have to do something more clever. You have to do something more painful. And so if you want to have logging in the middle of a function, you're going to have to do something special. In particular, we're going to create a function that returns not only the value you're interested in, but also a log. So this is just a tuple with the result value and a log attached to it as well. And so this fizzbuzz function is effectively just the identity. It takes n and passes n right back out. But it also computes fizzbuzz on n and passes that out as a log message. So what happens if we have a bunch of these logs that are being produced? Like I ran fizzbuzz over 10 different numbers. Now I have 10 different numbers and their associated logs. What do I do with that? I want to somehow print that out eventually. And what we're going to end up wanting to do is combining all those logs together into like the log of the entire process. And so we can sequence these values. So this function takes a list of tuples of the return value, which is, to be clear here, lowercase to mean that it could be any kind of value. It could be an integer or a string or another tuple, whatever, and your log. And it transforms that into a tuple of your list of values and their combined log. So really quickly, if it's an empty list, we get an empty list back out. If it's a list which has a head, then we take the value of that. And I guess what we first do is we take the rest of the things on the list, whatever they are, sequence them recursively to produce the list of the combined log from all the rest of the list and the combined values from all the rest of the list, and then we stick this first value on the head of the vals, and we take the first log and we append it to the front of the logs. And so what we've done is just recursively gone down the list, collected all the values, put them in the front, appended all the logs, put them in the back. So really quickly, I'm going very quickly. I want to make sure everyone can follow what's going on so far. Is there anyone completely lost? Any questions? Anything to? Is this going at a pretty appropriate speed? Okay, cool. So again, literally copying a sentence from what I said earlier. This is nice. This is wonderful. It lets us take these logged values and somehow do work over a whole bunch of them all at once in a more abstract and easy way. But the problem is that what happens if we want to log one value, or compute a value and produce a log, and then use that value to produce another log, and use the result of that log to produce another log. Like if they're sequential and dependent upon one another, then we can't create a list of all of them. We'd have to create them one after another, after another, after another. And so I'm going to, in a very parallel way from before, write and then log, which takes a value with its associated log, a function which consumes that value to produce another value and its associated log, and returns the total associated log. And this shouldn't be too complicated. It's exactly what happened up here. We break that tuple apart. We pass the a value into our continuation function. We get the resulting log and the resulting value. And then we pass back that resulting value plus our original log appended to the result of the continuations log. And so this is just one step of appending logs together. So, and then log. So the reason why I went over all of those things, it's a big splash of different concepts in different directions, is that they're all monads. And if everyone's familiar with how they work, if everyone's familiar with why this kind of sequencing is really valuable, if why you might want to use that, then you really have already understood monads. You've already understood every component of them. Monads are the abstract pattern of sequencing computations. And the way you do that is you use a function called bind. If we look back through all of the stuff I just went over, and then log is a bind style function. For prime is a bind style function. And then for maybes is a bind style function. That's all we need, effectively, in order to form a monad. So, generically, using something more akin to Haskell's kind of generic, or this could be any sort of polymorphism right here, where I'm referring to f as some kind of context, some kind of wrapper, some kind of container. It could be a list, it could be a vector, it could be an array, it could be maybe, it could be a binary tree, it could be an infinite list, it could be a tuple where a log is associated with the back. All of those different things are containers which allow us to write this bind function. And as soon as we have that, we have a monad. That's all. So the rest of what I want to talk about is mostly around how we can use monads. What are the different examples of them? Because effectively, there's not much more to say about what you're doing. What you want to see is just a number of different examples. You want to see this shows up in this circumstance, this shows up in this circumstance, this shows up in this circumstance, because at the end of the day, what we're trying to do is abstract over this pattern, the and then pattern, the bind pattern, see it in as many places as possible, and then be able to use the properties of that pattern effectively later. So if everyone's, do you have a question? Or?
No.
Okay, if everyone's okay with this up to this point, like, I'd like to talk about a couple more examples. Are there any questions so far? No? Does everyone have some familiarity with monads already?
One of the things, though, if you're writing in Haskell, you've got no choice. You're going to be using monads. You can write F# good ways without ever using a monad, particularly if you're not doing anything async. So that's one of the big unless everybody in here is fairly advanced and functional or hit some of the corners of F#, you maybe have never even had an occasion to use one.
Yeah.
You have something called computation
Expression.
It calls them different. So it calls them, in F# they're called workflows and monads. So, and the computation expression, monad is one kind of computation expression. But yeah, you can do a lot without ever doing a monad.
because you can change state.
Pardon?
You can change state.
Oh, absolutely.
Yeah.
You can change state if you choose to.
Yeah.
Okay. Well, I think if everyone's pretty familiar with what they are, and it's like, I feel like the examples I've been giving are really useful if you have never seen the comp script before and you just need to like start seeing the pattern. And these are very simple locations. But this is obviously not, like you said, nothing that I've done so far is anything that you would really like need to be aware of monads or use them, especially like states is an interesting example for Haskell because you don't have ambient states. You have to do everything through locally bound state, and monads form a nice pattern for abstracting that and giving you the appreciation as if state existed in a local context. And so I can talk about the specifics of that, but as far as F# goes, if you already have mutable state everywhere, then this might not seem terrifically interesting. The only advantage I would say in terms of why something like state is useful is that it allows you to tag in your types that this expression uses this kind of state. And when I've fed it, if I remove that type tag, like if you leave that stateful situation, then you could cheat using mutable state, but if you're being careful with it, then you might be able to say, I'm completely certain that that state that was being used in this typed area is not being used over here because I no longer see that typed tag. But I feel like in this sort of example, I'm probably not going to motivate a whole lot of stuff that you would need in F#. So I can keep going over this where I explain random state, but I'd like to adjust this to how people are, like what you guys are most familiar with or what would be most interesting. And at the end, like I said, if we can skip through a lot of this stuff, if everyone feels fairly confident, then it might be better to talk about some of the like advanced topics that I wanted to go over toward the end.
So like, you know, in Haskell, these are almost ubiquitous intrinsic
Mhm.
built-in. There are F# monad libraries that you can pull in, but there are only a few monads that are sort of built in with the core
Mhm.
distribution, like the one for asynchronous sequences, for
Well,
example.
the sequence also is a monad.
Sorry?
The sequence, the seq.
Yeah, but it's a
There was
special limited kind, right?
Mhm.
I mean, for doing a sequence.
The
The
option
ones that are more workflow oriented, there are only a few
Mm-hmm.
that are built in. Async is one. I mean, a lot of these support for async.
Yeah, I usually see it in
Is-
async when I
is
was like
one
looking at
built
F#
in,
stuff.
But you can write your own,
Mhm.
and you can use some of these libraries that have sprung up to do. There's implementations for state and you know, some of the other state patterns for logging and things like that.
Gotcha.
Yeah, so I don't know what people are interested in.
Yeah.
Sorry, you said that, previously I thought you said that link is a monad.
Mhm.
Could you clarify or just elaborate a little bit on that?
I'm not completely, I'm not the best person to talk about link, but the reason, in the examples I've seen of it, and I've not studied it extensively, I've seen stuff that has this and then sequencing,
Okay.
and also, as far as I know, link was invented by Eric Mayer, and he's explicitly said that he used monads to design link, so that's where I'm drawing that from.
Okay.
I wish I could explain better. Sorry?
What does link do?
You're in a room full of people who probably know a lot more about link than I do.
It's familiar with C#?
Not particularly.
Okay. What language are you coding?
Python, Scala.
So you're familiar with when you have a list that you're querying over, you just do filter map. So in C# before 3, we didn't have that effectively. So Eric Meyer built, first he added the Lambda capabilities, which was really just renaming delegates that we had before. But then he took it a step farther by genericizing the fact that, oh, well, you're going to start with your list, you're then going to filter it, which got turned into where, and then you're going to map it, which got turned into select. But then he even took it a one step further by saying, well, if the compiler recognizes your container has these methods defined, you can use this syntax for querying it, and the syntax looks like inverted SQL.
Okay.
Hence the term language integrated query, because if you can, in one context, you can write that, an entity framework, and I think even in Hardening it has that support where it will turn that into a SQL statement for you. In another context, you can have your in-memory collection, and it will process that for you.
Mm-hmm.
Similar to Seek, if you've played with any F#, the structure you write inside of Seek, open braces, is kind of similar to what you would do in
And that open brace thing.
But
is
the
where-
way you do it, inside a sync, there's a couple of syntax choices you can make. So there's a style of writing link that really looks like an embedded SQL statement. And somebody who writes it that way is gonna have no concept that I'm using a monad.
Yeah.
None at all.
And the primary place where monad shows up there is going to be in like the nested for loop kind of operation.
Right, and there's another style of writing a link statement
Like
that
the-
looks much more like, more lambda-like, and you can get a better sense of the linkage between, the syntax you're writing and what might be perceived, what's a monad.
Okay.
But it's not in your face, and I don't think for
Yeah, I
a
think-
C# developer, you would never hear that term.
Yeah, the majority of the
monad
time
with
people
respect-
use the monads, but I don't know the
Yeah, exactly.
Gotcha. Well, how about I jump to like a really cool example of using one then? I'm going to use Haskell again, but I'll
I
demo.
like cool example.
Cool example is perfect then. Use Haskell still, but we're going to talk about parser combinator libraries.
That's a good choice.
I love parser combinator libraries. They're beautiful. They have a really great expression as a monad. They'll demonstrate this syntax, the do syntax in Haskell, which is the let bang do bang syntax in F#. The computation expression. I looked that up.
Do you know of fparsec? Fparsec, you familiar
I
with that one?
know parsec.
Yeah, and it's a port parsec into F#.
Yeah, so I guess I'll be building fparsec. And it's amazing how quickly you can build that up and just start growing features and functionalities on that. I can like live code it in really, really short period of time and demonstrate how this is a use of monad. So what I'm talking about is a parser combinator library. And so what we're going to see is we're going to see types like this. Parser A equals something.
So can you talk about when you would prefer combinators versus monads?
Yeah, definitely. I think of monads, this is the other, maybe I should leave this to a question. I can give two really, really broad examples. I can either talk about free monads or I can talk about parser combinators. Parser combinators being fparsec, free monads being the command pattern in a monadic style. And very frequently I would end up using a monad if I have this command pattern sort of mentality where I'm setting a sequence of instructions and I want that sequence of instructions to be interpreted in some kind of way. Monads form a really foundational way of looking at sequences of instructions in the same way that I'm sequencing maybes with and then. Some people like to call monads programmable semicolons, where if I have a bunch of different operations and I'm going to break them apart with semicolons and I want that semicolon to mean something like, oh, there's state back here, pass it to the next expression, or oh, this could fail, throw your exception. That programmable semicolon notion is something that I find to be very monadic. To your point, one of the things that you might see with parser combinator libraries is there's a monadic style and an applicative style. An applicative style looks a lot more like functional programming, where you're just plugging arguments into functions, into larger functions, into making to a big expression tree. And there's something called applicative functors, which is really scary sounding, but it's a weakening of monads. There's slightly less capability there, which forces it to be more about this expression style kind of thing while retaining much of the power. And so you can build an applicative only parser library. And if you do that, then it'll force people to no longer build a sequence and think about sequences of operations, but instead be thinking about expression trees of operations. And the advantages of it are that you can get better logging, you can get better error messages, things like that. So if that answers your question to some degree, the sequencing of events is something that's really strong in monads. And one of the reasons you would use them, if I were programming in F# and I didn't need it to do state and I didn't need it to do all these things that you do need to do in Haskell, what I would use monads to do is to create a local context where some kind of sequencing is in play. That's what I'm going to do with parser combinators here. A parser combinator is a type like this, parser A, which means that you might see a value, x, is a type parser int. And what that means is that x represents a computation, which if I hand it a string, it'll try to parse that string and hand me an int. And so I'm going to talk about this as a monad because I'm going to be working inside of a computational context where I keep sequencing operations if I had a string, this will maybe produce something. If I had a string, this will maybe produce something. If I had a string, this will produce several different options and we'll follow all of the options and do a non-deterministic parse. And so because I'm building this specific computational context, and I want to emphasize that that's what's going on in this component, then I would use a monad, I would use types, the type system to ensure that that's the kind of thing that when I'm working with X's, I'm thinking about.
Can you explain, I'm sorry,
Yeah, sorry, that's kind of
not
hand
familiar
wavy.
with the term at all. What kind of, what's an example, or what kind of layer are we talking about where this would be a concept that's useful? Is it at like parsing, to parse, to take a 5 and turn it into a number 5, digit 5? Or is it something like taking a code abstract, turning it into an abstract syntax tree?
Yeah.
Or is it like documents and,
All of those.
All of the above, yeah.
Yeah. You can build, like, a lot of times when you're building a parser, you're going to try and build, like, a BNF thing. You're going to try and use, like, Antler or something like that. This generalizes all of those. It's maybe not always as nice. Sometimes it's nicer. But people use AutoParsec, which is just a faster version of Parsec, to parse, like, binary packets in network transmission. Or they'll use Parsec, which is nicer error messages, to parse a DSL that they're writing, or a document that they're writing, or make an XML parser or something like that. Really, this is what you're going to see. If we want to parse an A, what we're going to do is we're going to pass some kind of parser to a function. We're going to give it a string, and it's going to give us maybe that A value and whatever the remaining values of that string are. So, like, let's say we have parse int, which is a parser of integers. If we do run parser parse int, that's the type string, maybe int to string, right?
And sorry, the syntax of this
Sorry,
is that run parser is of type, and then there seems to be a significance of uppercase, lowercase.
Yes.
So the lowercase a is a
Type variable.
generic,
Mm-hmm.
okay? And do we do one parameter at a time, like parser of a is a single parameter, like you can only have one parameter?
You could have many. You could do a parser that takes in s's and returns a's, and then this would be an s.
Okay, and so when we have a parser of a
Sorry.
that gives a function which takes a string and returns a maybe.
Yeah. It's taking a string and maybe turning it into a value of the type that it's trying to parse. And if it cannot, then it will fail with nothing. No problem. So down here, if we have parse int is a parser of integers. If we pass that to run parser, then we get a function that takes strings to maybe an integer and the remaining string. If we do run parser parse int 5, then that will give us the value maybe 5 empty string. If we pass it 5 foo, then it'll give us 5 and the remainder there. If we pass it just foo, it'll give us nothing.
And you could do this on a stream as well somehow, if it were more abstracted, where it would return the rest of the string, the rest of the string.
Yeah. Really, the actual Parsec library operates over anything you can pull characters out of. It could be a binary string, it could be a linked list of characters, it could be a stream of characters coming in some way or another. Yeah. So that's the idea of a parser combinator. We're working with these kinds of objects, parsers that produce A's, and we can run them by giving them a function which takes, or passing it to a function like run parser, which then requires a string and returns maybe the result. So because this is the behavior that we want, right here, string to maybe a value in the rest of the string, we're actually going to implement it exactly like that. So we're going to say is data, a parser of A is equal to a string, a function that takes a string to maybe A in a string, or maybe A and the leftovers. And so some Haskell syntax here is that gives us a constructor, so let's call this a make parser. And then we'll go ahead and write run parser immediately. Run parser has that type, and it pattern matches on make parser and returns that function inside of it. So all I did was just rename that string to maybe value function as parser A. So we can immediately start writing parser types. So for instance, parseInt is easy to write. So we're going to make a parser. So we want to provide the constructor. And we're going to define this parser, which is just a right? Does everyone see what's going on here? I want to create a value of a parser. To do that, I'm going to use the constructor makeParser, and I'm going to pass it a function. That function has to be this type in order to make a parser. And so I'm creating a where statement, which is just a let statement. And I'm going to define this parse function down here, where my ellipses are. And we're parsing an integer. We're just going to parse a single integer off of a string, in this case. And so all we want to do is we want to start looking at the strings over here. If the first character of the string is 0, then we're good. We can return 0 and whatever the remainders were. Pretty simple. If the second character is a 1, we can return 1 and the rest of the characters. And we obviously can do that for all of the different numbers, which I'm not going to do because it's just a bunch of repetition. At the end, if it was anything else, wildcard, if it isn't 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then we can't parse an integer off of this string, and we'll return nothing. And so all of this is just semantics of what a parser combinator is. It's a very simple one written directly. The type of it is a parser combinator that produces integers, and it does it with this function, which does a really stupid, like it parses an integer about as simply as possible, and isn't very complicated.
But you would only do that, I mean, just for practicality, I want to cover this because you're only doing this for the digits. You're not doing it for 10, 11, 12. You're only doing it for the digits. And then you have, how do you then shift everything over when you read the next digit?
And that's exactly where the monadic component gets into it. Because what we want to do is we want to parse a digit and then parse more. And when we get that and then in there, we're going to start seeing the sequencing in the monadic components. So right now, this is not yet monadic at all, but it's just trying to get out the idea of what a parser combinator is doing, what the domain that we're talking about right now here is, and how to interpret this type.
One of the things that's interesting about the latest version of the F# port is it doesn't use monads, it's combinators throughout.
Oh, it's just that.
And it has operators to chain together, sequences of parsers.
Is it the applicative?
Yeah.
Functor?
Yes. Yes. And so the first version used monads a lot. Second version, he took them out.
Yeah, and like I said, if you use applicative functors, you can get much better error messages.
And that was one of the reasons.
Yeah.
And performance was another reason.
Yeah, exactly. It corresponds to a different kind of parse as well. So it's not as general. It's a little bit harder to use sometimes, the applicative functor format, but it's definitely faster and definitely uses better error messages, or produces better error messages. Effectively, the difference when you get this applicative form is that you're allowed to look over the entire parse, everything that's going to happen in the future before you start running it, look at the structure of the parse and say, here are all the places it can fail. I'm going to produce good error messages, make sure that I keep like the point in the string when I hit all of those different places, or I'm going to keep the history better. And it just allows you to have better, the implementer of the parser can be more creative to use that structure. But with a monadic structure, the person who's actually using the user of the library has more flexibility to write more complicated parsers.
Can you just clarify the difference between combinator and monad?
Yeah, so effectively what I'm going to do is, let's say, well, I'll use your example where we'd like to parse 2 integers. Really not great, but okay. And this will be int, wonderful, which is not great, but it demonstrates the example of we can chain parses. And so Parse to int is now really easy to write because we have parse int. If we have a monad instance, which we'll get to that. So what we want to do is we want to parse the first one, parse the second one, and then return them like that. And so this do notation is the let bang computation expression F sharp notation. Very similar thing. In F sharp, I guess it would just look like parser. Something like that. So do notation is just Haskell's form of this exact same thing. It's just a syntactic change. So here we can see exactly. The monad is giving us this notion of sequencing. Parse one int, parse a second int, and then return the two ints together.
But isn't that a combinator?
And we can write this in combinator format, like this. Parse two ints, parser int. Let's call this package. What we'd like to do is write this.
No, so the combinator is the bind.
Yeah, but the applicative, I mean, combinator is a really ill-defined word.
Okay.
Like it's well-defined if you talk about like SKI combinators or something like that, but in terms of like programming languages, people tend to use it whenever they want. But in terms of like the applicative functor notion, what you'd like to write is like this, where it's just a function, where let's say package is this, where package AB equals AB.
Yeah, so package is the higher order function. It's taking two functions and doing something.
Well, the real higher order functions, if you, this doesn't work directly, because the type of package.
In F sharp, that would work.
Oh yeah. All right. Well, in Haskell, we're going to keep track of the fact that each one of these parse ints, is of type parser int. And package down here is of type A, B, AB. So if you were to run this as is, the type of this total function would not be that, it would be that. And the problem with this is that we've never actually sequenced those two parsers. Like, we just have to next to each other, but we haven't combined them together and said you come first and you come second. And that sequencing is exactly what we're trying to capture with monads, with parsing one integer after another. So the applicative functor format looks like this, where all of these weird $ and multiplication symbols are just their function application. And that just, in the same way that you want to have like a programmable semicolon, if you want to have this combinator style, applicative functor style thing, you need to insert a function in there, insert an operator in there, which will do function application for you. So I don't really want to go into applicative functors per se, except to say that you can do all of this stuff with applicative functors. They're very similar to monads. They're a little bit weaker. They give better error messages and better performance in some circumstances.
And those are what F-Parsing is using extensively.
So yeah, if you what I'm going to demonstrate with the rest of this is not F-Parsec, but if you use F-Parsec, then you'll see something in this format instead. And again, like you can see that it emphasizes the idea of a function application here, whereas up here it emphasizes the idea of sequencing first, then second, then return. So we're going to keep going with this. Parse two integers, great, we can parse two integers. Another thing that we might be really interested in doing is parsing over and over again as often as we can. So parse many. What we want to do here is we take a single parser, such as our parse one integer, and we run it once and again and again and again, producing a list until it fails. And so for parse many, what we'll need to do is say do head. We pass it a parser. So we run that parser to produce the head. Then we produce the tail by recursively calling it. And then we return the composition of the head and the tail. And so this will parse over and over again and parse a whole list out. So, where was I? What I'm just demonstrating here is these are uses of do syntax, uses of bind, uses of and then, the sequencing notion in order to build more complicated parsers out of simpler pieces. And so like another example you might see theoretically is if you are parsing like a network packet of some kind, like you might parse the header, parse the body, parse a checksum, and then return some combination of those. And so what we're doing is we're building up a language of different kinds of parsers. Right now I have a parser of ints. I have a parser of a pair of ints. I have a parser of lists of things, repeated parses. I have a parser of network packets. And when you're using parser combinator libraries, that's what you end up doing. If you're building a parser for an AST, you'll parse each literal independently, and then you'll parse the a literal, like it's any one of those literals will be successfully parsed by this combination parser. And then you'll parse an expression of like a numerical expression, and then you'll use that to build your parser of statements. And then you'll make a list of statements, and that will be your parser for your whole language. And so you just build up more and more complicated parser combinators recursively until you get to whatever the whole complicated parser that you actually want is. So that's the idea of the parser combinators. Are there any more questions about the general idea? I can maybe demonstrate a couple more examples of parser combinators. And then what's really missing here is the glue that ties it all together. Like, how am I doing that? How did I use do syntax? How is this a monad? What is the structure behind that? So, is there any questions about what a parser combinator is and how you use them? No.
I think generally I'll just say reasoning compression is kind of like an iterator in a function, kind of probably very flexible, very powerful, but it's like an iterator, enumerator or whatever for a collection, through a collection. Is that a kind of?
Yeah, you could.
Well, I mean, except for that, right, that differs, right, because you can have, as you're saying, there's this collection, right, you're collecting the values, so you can do the calculations and you're passing those calculations through. So while you're doing iteration, right, iteration implies several things, that it's a bound collection, right, it's not an unending collection, which I think you guys support, right? So, but the general theme, right, it would be correct, wouldn't it, that yes, you're trying to sequence, you're trying to stream over a sequence.
Yeah.
But that's where everything else falls short, because we're unable to collect the previous values and
feed it in.
Exactly, and feed them to the next iteration.
And I would say the iterator concept is actually exactly that for loop example I gave before. With lists in Haskell, they're generated lazily, so they work very similar to iterators. And what you might write, if we drop the parser combinator example for a minute, you might write in do syntax the iterate x's. Return some combination of that. And what this means is for every x, iterate through the entire y iterator and apply that function to that combination of x and y. Then do the next x, iterate the entire y iterator, do that function again. And when you get a bunch, you're going to get a bunch of these different results. Combine them all together and create a new iterator of all of those results.
Okay.
And so iterators form a monad exactly in this fashion.
Okay.
And you could probably write a computation expression that looks exactly like this over iterators. Is that the seek thing?
I guess it's fairly close.
Okay.
But the other thing I see, at least the way I'm used to using monads in F sharp, is you're writing sort of the happy path in the body of the monad, if I can use that expression. And when things go badly, it fails,
Mm-hmm.
and you don't work all the way through.
Yeah.
Does that make sense?
Yeah, totally. That's happening
Maybe
down here
monad.
with bars.
Pardon? No, it's
So
not
may-
just a maybe. So let's say it's a custom one, an arbitrary one you've written. And so you're writing, you know, first step went well, second step went well, third step, no. So it bails. It doesn't go the rest of the way through,
Mhm.
which is extremely valuable.
Yeah, I mean, there's also the error monad and Haskell.
Yeah, it's explicitly for
It does that,
errors.
yeah.
And, but even, you know,
But-
not the error one. I'm writing a totally
But the
custom
other
one.
thing
I've
is you
got
could
some
be
workflow.
accumulating stuff in the background without
Absolutely,
seeing
yes.
it.
So you can be, you know, if there's housekeeping that you need to do on the
Right.
side between steps, you can do that. And it can clean up a lot of the clutter
Yeah.
that you would normally, where you gotta put a lot of boilerplate around something or the other. You can clean that up, tuck it away someplace so it's done consistently.
I would say that's exactly
Yeah.
a good example of what's going on with these pars ints and pars two ints
Mhm.
thing. Like, normally if you were to build a parser, like, you would have to handle all of these errors. Like, I
Yes.
want to parse one integer. Okay, I succeeded. Here's my success path. Oh, I failed. Here's my
Yes,
failure
yes,
path. Clean up, write out your errors, figure out what the leftovers are, all of that stuff. But when you express it with a monad here, all you have to do is just express, as you said, the happy path here. We parse one integer, we parse a second integer, we return the pair. All of the failure notions, all of those things, are all tied up in how the parser is implemented. And we don't worry about that. All of that behavior is handled automatically by the notion of what sequencing means.
Yeah, so the author of the monad took care of all that
Yeah,
stuff.
exactly.
And the user of the monad gets to focus on their happy path.
Exactly.
I have a question about the parser aspect. When I've written, what's it, LL1 parsers or whatever, like, I have to, like in your situation, the example you gave, it's a strict, like, we're expecting this, and we're expecting that, and we're expecting that.
Mhm.
But if you're parsing some code where you might have a couple of different options, like what is the thing that's following?
Yeah.
With the kind of parsers I've written before, it's almost like in the parent, you're detecting which kind of thing the child is based on, you know, the look ahead.
Mhm.
Is it the same, like how do you, is there a look ahead, or is it something that the child says, no, it's not me, and the other child says, no, it's not me, and the third child says, yeah, I just want me?
Yeah, that notion, I was going to try to avoid it because it's not directly the monad notion, it's an extension on top of it.
Okay.
Where you call it alternative or you call it monad plus, and you, in an actual parser combinator library, you would see that written like this, pars int or pars character. And effectively what this guy is going to do is he's going to examine the first one, see if it succeeds or fails. If it has failed, then it will move on to the second one. So it's a left biased recursive descent or alternative descent. Again, I'm trying to sort of balance out between making like all the features of a parser combinator library and
Yeah,
trying to
sorry,
make
I
all the
just-
features of monad, but that's an extremely important point, and one of the nice things you get with monads is that you start with this base structure of and then you layer on top of that the notion of, and this thing has state, and this thing has failure, and this thing has the ability to be combined and processed sequentially or in parallel. And so you can start to build up higher and higher levels of abstraction off of that, but it all begins with monad because that sequencing is such a useful core aspect of everything. So I think the major next thing that I would want to talk about here is just how we can actually get this kind of behavior. Like, what is actually going on when we do this do notation? The first thing to talk about there is that we're going to desugar the do notation. So we'll write parse packet again, prime, where we've desugared this do notation. And so we'll use our friend bind before. In this case, it's going to be bind parser. Or in Haskell polymorphism, we can just use the same word, but it's just polymorphism. So we're going to say bind parse header, and we're going to create a function of header. And then in this function, we're going to bind parse body, and we're going to bind to it a function that has body. And in here, we're going to bind parse checksum and pass it a function that has checksum. And then at the bottom, return packet header body checksum. So that's all do notation is doing. It's just making this piece less annoying to read. And the rules of do notation are like what I just said. You convert these backwards arrows to this piece, this piece, and everything below it. Or this piece is your bound variable, and this piece is your function body, right? You just do that recursively. Bound variable, function body. And that's the same thing with the let notation. Bound variable.
So it's like the Haskell has a closure, sort of like a closure.
It's exactly
Is
a
that
closure.
correct? Okay.
Yes. So something like that with flat notation. So if we want to implement monad, then all we have to do is we have to implement this bind here and this return down here in a way that causes us to sequence parsers appropriately, carrying over all of the, like, passing the string along as implicit state, collecting errors when they occur, and making sure that they stop at the right time. And so all of the magic is happening in the library implementer, who has to define, return, and bind. And so we'll do that up here. We'll start with return. Return has a type like this. It takes any value and injects it into the parser. It doesn't actually parse anything. It's very important that returns don't actually have any effects. All they do is take pure values and wrap them in the parser in as boring of a way as possible. And so in our case, it'll be a parser that always succeeds, always returns whatever the wrap value is, and doesn't consume any of the string. And so if we have this value, and we want to make another parser, parse. This function is again just going to be string to maybe a string. This doesn't actually work, but I'll ignore that for now. That's effectively what the type is. And what we're going to do is we're going to take the input string, and we're going to return just the value from up here that we got passed in, and immediately return that input as its output. So we succeed because it's just. We ignore the input string and immediately feed it to the output without doing anything to it. And we return whatever value was given to return. So this is the most boring parser possible. It does nothing, and it just returns the value. And then we're going to define bind, which needs to sequence parsers. It needs to do one parser and then do the second parser in order. So the type of bind, which if we go back over here, they all have the same type. They all look like this. So the type of bind, F is going to become parser. So we have a parser, we have a continuation, and we need to produce a parser down here. So to do this, we need to run the first part. Well, let's talk about what we're trying to produce. We're trying to produce a parser, so we know that we're going to need to use the constructor. And in here we have the input string, and we need to produce a type of maybe B string. So we need to make our way all the way down to getting B's. And this is one of the nice things about typing in Haskell and F# is that when you know your types and you've got all that structure laid out, like I knew I was going to make a monad, I knew that I needed that notion of sequencing. So I wrote down that I needed to write the type bind, and then I'm just going to, I don't have to think anymore, I just need to figure out somehow I need to get a B and return that B. So the only way I can get a B is by using continuation, because that's where I get the B out of this parser. And the only way I can use continuation is if I have an A. And so somehow I'm going to have to get the A out of this original parser in order to get my B. And so it just becomes a puzzle. So let's use pattern matching to unpack this first parser. This is now we have a parse function. And this parse function is of type a string to maybe A in a continuation string. And down here, we've got an input, which is of type string. So if we give that input to our first parser, then we're going to get out a type maybe A in string. So we can capture that, use pattern matching again to collect our values. So we'll case on that. If it's failed, if the first parser fails, we get nothing. Then we're going to want the total parse to fail. So if we remember, this function right here is of type maybe B or string. We can obviously produce a maybe value just by giving nothing. So if the first parse fails, the second parse fails, is what that's reading as. If the first parse succeeds, then now we're going to have a B value, or we're going to have an A value, sorry. And we can pass that to the continuation to get our second parser. So we can, this is valid now. And that's of type parser B. Is everyone following along right now? I'm kind of making a big mess, but are there any questions so far? All right.
That's very good.
All right, cool. I'm glad. So now that we've gotten the A out of the first parser, we can pass it to the continuation to get the B from the second parser. And we'll need to pattern match on that. So we can say let make parser, or sorry, let make parser. This is a second parse function, continuation A. Sorry. If the parse succeeds, where we're at, then we get A and the leftovers. That's actually what I wanted to write. Right. There's a missing piece. A and the leftovers. If we pass an A to continuation, then we're going to get a parser, so we can pattern match on that. And if we pass the leftovers to this new parser, then we're going to get another a maybe B string, which is what we want. That's the whole thing. It's kind of messy. Is anyone struggling to follow along or have any questions about this at this point?
Can you explain the let in? Is the let just pattern matching and then saying?
Yes. Let is just
So you can destructure the returned parser and use the function?
exactly.
Okay.
And the reason is because we're inside of a parser down here, right? We have to produce a pass to make parser the function, not the parser. So we need to pull this layer of make parser off of it in order to return the function and have the types line up. So yeah, that's all the let is just destructuring that layer. So that's fine. It's a mess because I kind of went through all the pieces piece by piece, but we can see that what's going on here is if the first parse fails, the second parse fails. If the first parse succeeds, then the leftovers from the first parse are passed to the second parse and we just continue the chain on. And so this is providing exactly that notion of sequencing, of parse this and then parse that. And so with that, and if I get rid of my notes here, that didn't quite work. With that, we have all of what we need to do the parser. I think without getting into the polymorphism of Haskell, this won't compile quite yet, but by using return and bind and exactly the pattern down here, we're allowed to sequence parser after parser after parser. We can build more complicated parsers. We have that notion of sequencing and failure all being collected. And we just have to write out parsers in this do notation like that in order to build them. So we get clever syntax, we get sequencing, and the user of the library doesn't have to worry about any of how parsers fail or succeed. So, are there any questions about what's going on here so far? Cool. I think there's like a lot to take in when I'm just describing this outright, but I think what I really want to leave you guys with is not so much the details of this, but instead the notion of what I just wrote out. I am up here, above my comment line here, is what the library writer writes. He writes the notion of what is a parser combinator, how do you sequence them, how do you combine them, and what are like some basic primitive ones like parse integer here. And then the user of the library can use this nice syntax to build more and more complicated parsers up from the pieces. And so that's the functionality of a parser combinator library.
Is this one gonna win?
Yeah.
So when can you go up a little bit?
Yeah, of course.
The thing, the one you just worked on. So the bind operator that you're making here, or the bind function that you're making here.
Yes.
You only have to make that once. Like that's for the entire Parsec library. They would have just made a really great full-featured one of those.
Yep.
And then because of that, you're now able to do what you just said, which is you can then start building up in a simple syntax that all these chain together operations exist. So
Exactly.
that's really cool.
I know he didn't want to get into it, but if you define that bind correctly using what's called type classes, there's a monad type class. If you define the right notation for your monad, then you can automatically use do notation with it.
Mhm.
Otherwise you can't. So so the additional step would be make his parser officially a monad in Haskell terms by defining both bind and return. And the bind looks like what he just wrote there.
Yeah.
And then telling Haskell that parser is a monad and this is the meaning of bind for the parser, and this is the meaning of return for the parser. And then you can automatically use do notation,
So like,
which makes it look so much nicer.
yeah, that was why this wasn't compiling before, because I was using do notation down here, but I hadn't actually told Haskell that this is a polymorphic instance of monad. But you can't do that in F# anyway.
Yeah,
so
right,
there's-
F# doesn't have type classes, that's one
Yeah.
of those.
But that's really confusing to beginners because every monad uses that same operator, greater than equal, but it means a different thing in every monad, and you don't necessarily know what monad is getting inferred. So that was a problem for me.
Yeah, that's always hard, because if you're looking at like someone else's code and you just see like do la la la, a whole lot of
Yeah.
lines of this. And if that's in the middle of a big function, it can be hard to know what
Yeah, what
the
does that
actual
arrow mean?
context of that is, because it's so polymorphic, that syntax. But usually, if you're able to track down what the types are, which can take some effort if it's like buried inside of a function, and good Haskell style, I imagine good F# style probably is very similar. Like at the very least, all of your top level definitions probably have a handwritten type signature for documentation.
Only to
purposes.
find out if you figured out the same thing with the compiler figured out.
Yeah, exactly. If you completely wrote it wrong, it will yell at you and say like, no, you got the wrong idea here, dude. And that will be that's really helpful for being able to track out what this notation means if you don't actually, because like you said, like this is very, very generic. It translates to a very general space.
Yeah, that backwards area in do notation, backwards arrow in do notation is just bind.
Mhm.
Yeah, what's just kind of like a tool question, right? Is there a tool that kind of help you with that? To tell the
There-
type, like in the middle of the code?
We'll certainly complain if you do it wrong.
Yeah.
Okay.
Like I said, the common style is
You're
to
doing it.
float all of your type declarations up to the top and make sure that it's all consistent. Like, I think this type will be a parser of integers. The compiler agrees with me, so I must have been right all the way throughout that whole system. There's also a number of different IDEs. Like, there's not IntelliSense where you can just like have it spit out all of the different members of a type or something like that, but you can ask the primary Haskell compiler, GHC, you can ask it, what is the type of this fragment in context? And it will say, oh, the type right here is parser, so that's what do notation means right here. So all that information is available.
Is there an IDE that you like?
Emacs. Not, I guess not IDE, but Emacs.
Yeah.
Is that what you're using right now?
Yeah.
Okay.
And this is giving you Haskell specific syntax coloring, right?
Yes.
What is data, what is the data keyword there at the top?
Define a type.
That's actually the line I'm having the hardest part on,
Yeah.
is the make parser, and I know that's back at the beginning.
Remember the record notation that he showed us? That's what it is.
Yeah.
Except in Haskell, you need to type a name on the left and on the right.
Mm-hmm.
So it's saying that there's a type called parser, which is parameterized over any type A, like parser int, parser string, etc. But that's a type. To create an actual example of it, use make parser.
Yeah.
That's called the data constructor.
Okay.
So when you say make parser and give it a function of that format, string to maybe a comma string, then you get a parser. And if you give it a function that goes from string to maybe int comma string, then you get a parser int.
Yeah.
And with all the other things that can be named the same, how come make parser has to be named differently?
It doesn't have to be.
It doesn't. I was just trying to emphasize the constructor notion like that.
Okay.
But then you can have types defined by data that have more than one constructor.
Mm-hmm. Which is your discriminated union. Again.
Right.
Yeah, so to give a really quick overview of the Haskell data type syntax, like he's just saying, you can define a type with T. It can have some type variables, which is parameterized over, which are all lowercase. And then over here it has a constructor type, which has some argument. There can be multiple constructors.
But you have to use the A, B, C, or D over there.
Yeah. So arg1 would have to be something like A, B, C, D, all of the a tuple of all of those things, or like A and an integer. And so in order to construct things of type A, B, T, A, B, C, D, you can use C as a function, which constructs the T like that.
No. Can't be a tuple there.
Yeah.
No, it's gotta be arrows.
Right.
In your A, B, C, D tuple, you gotta go A, arrow.
No. It's just a tuple up here.
Oh, right, I'm sorry, yeah, you're right.
No worries.
Right.
And to construct a T using D, we could give it an A, an integer, and it would return T, A, B, C, D. So that's creating your discriminated union. You have two ways of constructing type
Where are you
T.
getting the C and the D?
They're
Your second statement?
named right
D
here.
and the D constructor.
The second statement? Oh, those will be left generic. So let's say I type D, like foobar 3, right? The type of that will be T string BCD. It doesn't know what they are yet. It will have to figure it out some other way. And so if I use that in a context where B, C, and D are bound in some way or restricted in some way, then the inference will flow back into this type and figure out what B, C, and D were. But for now, they're just generic type variables.
What is the difference between data and type?
Type creates a type alias, and data creates a new data type. So this is actually completely invalid. I would have to do data parser and then explain what parser is. But if I were to say like type string, I keep using string everywhere. is literally just that. That's the definition of string. It's just an alias of a list of characters.
Okay, now I kind of have my mental map now, because in F sharp we have one keyword to represent both of those things.
Yeah.
That is what is, yeah. In F sharp you have type, and you write that, and you're aliasing exactly like you explain it, and then you would type again, and then you do the choice, the bar there,
Mhm.
and you get the same thing, but it means it's now something, it's doing something different. It's declaring the type
Gotcha.
differently.
But in Haskell, if you say, for example, type name equals string and type address equals string, the compiler can't tell the difference between the two.
Yeah.
But if you said data name equals name string and address equals address string, then you can't accidentally mix them up. Because they're different types.
Yeah. There's a nominal typing component only in data.
That makes sense.
That's one of my favorite things. Just my first exposure to that concept is in F sharp, and I absolutely love it because in other languages, there's so many times when you've got like a number of, you've got time is the worst one when they say it's a timeout, but it's like, is it in seconds or is it in milliseconds or is it in
Yeah.
inches or whatever else? And it would be so nice if you could specify that this has got to be
Right.
a string type without having to wrap it with some stupid, class or something like
And then you can write conversions between them
that.
if you need them.
Question about monads. How do you, so in any, medium, I guess, to large program, you're gonna be employing a whole bunch of different monads.
Mhm.
How do you combine them?
That's
How do you what?
How do you, you're eventually gonna have this function
That was one of
has
his
to do-
advanced topics.
Okay.
yeah.
One of the three advanced.
It's worth really talking about that though, in the sense of this parser, which is now a mess because my examples are all over the place, but parser can be seen immediately as a combination of the state monad and the maybe monad. If we had looked at the definition of those two monads as types and the definitions of the binds, they really both exist right there. Like if we look at bind of our parser here, this nothing to nothing and just to something else piece, that's the short-circuiting notion of the maybe monad. It's exactly the same code. The take the input and pass it into some continuation in some method or another, that's exactly the state monad. And so there's actually, it's it's one thing to look at this and say like, oh, it's doing the same thing. It's actually principled enough that you can have, you can take the state monad and the maybe monad and combine them as objects in the type system, create an alias for that like monster amalgamation and call it parser and have all of the code be written for you. Like it'll just use the underlying binds of those two types. Like literally I can write it right here. Here's another way to write parser.
In Haskell, you can do this.
In
Because
Haskell.
this is you don't have the same generic capabilities for monadic combinations, or that you do in Haskell. F sharp just doesn't support that.
There. That's a parser combinator written as efficiently as you can in
You
Haskell.
can't do that in F sharp.
You still have to write all the individual parsers.
Yeah, you have to write parsins. You have to write your
Right.
foundational basis.
So is
response.
parsec, is that the type of parsec?
No, there's more mess to it.
Okay.
Parsec
More-
also has error messages in
Right.
it, and it does backtracking in a different way.
So you use the list mode?
It used to use the list. I think they changed it. Actually, really annoyingly, it does everything in continuation passing format because it's faster. So,
Means nobody can read it?
yeah. But you don't need to. I think that's actually valid code right there. So, in terms of what I was just saying, in Haskell, so this doesn't really apply to F sharp, except in the sense of monads are composable in this kind of way, and if you want to think of at a high level, I want to compose these different features of monads, like I want state here, and I want continuation passing here, and I want non-determinism, and I want to build a context where all those things exist. Monad transformers allow you just to jam them all together. In Haskell, it's this syntax, and you're pretty much done. It's actually this, but I don't want to get into what new type is. It's just data. It's data where deriving works better.
But you could have used data there.
Yeah. Well, I can't use deriving then.
So what
Oh, you
derive-
can't?
No, it needs
Oh.
generalized
I
new
didn't
type
know that.
deriving only works over new
Okay.
types.
So just what the driving does here? So I know there's
Yeah.
two.
It tells the compiler to figure out the bind and the return from monad, and the F map for functor.
Yeah,
And it knows how to do it,
Okay.
which is pretty amazing.
yeah. So so it's,
Well, it's type classes that let it do it a lot of
Right.
that, right?
Yeah.
I mean,
Yes.
well,
And
particularly new type creates an isomorphism between two types. And so it's just saying functor and monad. Well, this piece down here is a functor and a monad. Why don't you just steal it? And it just injects that into the type class and allows it to instantiate that. But what's really neat about this, in the sense of I'm going to build monads just by combining these different pieces together, that this concept called monad transformers, by the way, if you want to look stuff up. And one of those resources I have in there is monad transformers step by step, so I highly recommend reading that.
That really helped me.
It's a really great article. So this is a deterministic parser, because I've used maybe. Maybe is just the monad of failure. Now it's a non-deterministic parser, because I'm using list, and list allows me to traverse many different opportunities and do them all in order.
And now, you can't see it, but that box is just open bracket.
Yeah,
close
it's just list. I should write it like that, even though it's not valid.
You've done this in such a terse way, but, and I think it gets a larger question I have. Is there overhead associated with you having written it in this combining way as opposed to writing it the way you did originally?
There is a little bit of overhead, yeah. This new type thing helps to prevent some of that. New type, when you actually compile it down, it erases, like the type distinction remains, but when it erases types in the compiled code, there's no data distinction, it literally is the underlying thing. So that has removed a little bit of overhead, but the stacking of monads is always going to be more expensive than if you actually stack them all together manually.
And if you're using monads all the time in all your code, and you're not necessarily making a specific type that the compiler can, I don't know, squash down for you or whatever. Like, is there a performance hit to using Haskell compared in a way of pure computation, even though it might allow you to organize your code in a way that's more efficient in the first place?
Mm-hmm.
But is there like an overhead associated with Haskell at all?
Yeah, Haskell's really amazing, and their compiler team's just ingenious. A lot of the time, they're able to make really efficient code from a very high level description, but there's definitely an overhead of some of these like complex types, because like at its most basic, if you write a data type with a constructor and there's some set of arguments to that constructor, each one of those is a pointer in direction, and that has to go track down, and there's a little bit more metadata. But a lot of the time it can actually figure out that you don't really need that interaction, and it will eliminate it for you. The other major Haskell performance you get is the immutability and lack of ambient state means that you're going to have you're pretty used to the idea that you can have O1 access to memory, like from a hash table or something like that. Generally, in a pure functional setting, you're going to have a binary tree, and everything is going to become log n on that. It's not as big of a disadvantage as it initially sounds. Like, you look at all your asymptotics, and it's just like, oh, everything got multiplied by log n. Great, thanks, functional programming. But in a lot of cases, when they use Patricia trees, it's like basically a constant as well. The log is such a slow growing function that it's almost constant naturally. It's like log base 32 and something like that, log base 64. So there's a lot of tricks that they do to make it pretty efficient, and you can get surprisingly efficient code out of it. If there's more I can talk about later, but I think that's a fair overall description.
Cool.
Cool. So I would really like if there's any more questions about other things that are related to this, monad transformers or things like that, I'd love to field those, but I feel like I've given sort of a slapdash approach to a lot of where monads come from and how you can use them in at least this particular example. So
Can you say a couple things about the free monad?
yeah, it's I can say a lot of things about the free monad.
Or just
Yeah,
at least show us a hint of it?
The free monads really is. I said at the very beginning of this slide that monad's never a noun; it's always an adjective. This is the one time it's a noun. The free monad is a very fundamental monad. It's the most basic monad of a certain kind, and so where you would see a free monad is, let's say we're going to implement the state. What we do to implement state is we think of state as a thing where you can get a value and you can put the value back. And if you get it after you put it, then you're going to get back whatever you just put in. And so we're going to write that set of instructions like in a kind of convoluted form. So just notice that all I'm going to write here is get and put. So we have a discriminated union of type with get and put. We have state f over a type s, and get's going to return that s, and put's going to
It's not gonna look like the regular get and put?
it will, with a little bit of massaging.
No.
I'm trying to think of how to approach this from a very high level without getting into the weeds too much. Effectively what happens is you write a type which describes the different operations you can do. So monads are giving you this context where certain effects are in play, such as fail now, get state, put state, parse this, parse that. You write all these different instructions out. And it's like I said, it's like a command pattern. So you're going to create a type that represents each one of these different commands. And you're going to sequence them one after another in a monadic form. Like that gives you the natural notion of combination. So if you have like, let's say you're making a command pattern, you built 3 commands, and you want to run them one after another after another. You have some notion of sequencing right there. You can have that be monadic sequencing, and if you do, then you get a lot of nice properties about how monads work directly baked into your command pattern. If you have 2 sequences of commands, you combine them in the same way that if you had 2 commands and you combine them, they happen one after another. You also have the ability to talk about how variables get bound in the middle of a computation. So where this shows up a lot is if you're writing an AST and your AST has variable binding happening inside of it, that variable binding can be captured entirely in how monads work as well. So it's very, very useful for writing like an embedded DSL, which is what I've been doing at work. You write a free monad, you write a structure which describes all of the operations that could happen in your free monad. You convert it very naturally into a free monad, like there's just a way to do that. You don't have to think about it. In Haskell you do it in one line because the compiler will do a lot of work for you. You use monads to structure a computation over that set of instructions, and then you run it later. And your run function, the thing that runs it, could be run this in I/O where you actually go and do all the actions, or run this in a simulator where you like pretend that you're talking to somebody where we're actually sending back random responses, or run this in an analytic function which looks to see for how many times did you change the state, or something like that. And so the free monad is really nice because it represents this set of instructions, and it also allows you to choose many different ways of interpreting that set of instructions as a separate component. And so that's why I call it the command pattern in monadic style. You use monads to structure how those commands get put together and how they get executed at the end. And from a theoretical point of view, if you have the free monad over an instruction set, it's the best representative of any monad which can implement that instruction set. And so you have some really nice theoretical ways of looking at how the free monad becomes those other monads, or represents those other monads, or interprets them. So that was that really quickly. Hopefully that made some sense. Is there anything else any other questions or any other things you want to ask about monads?
We can wrap up here then.
Yeah.
All right. Thank you so much.
Would you